Alright, in this video I'll try to quickly get through the basics of intermolecular forces. You're going to come across this from a practical perspective in trying to assess melting point and boiling point. It's going to be important for reasons other than that. Obviously chemistry requires two molecules to come together and interact before they react. So the amount of intermolecular forces, the strength and type of intermolecular forces between two molecules will have a large effect on their chemistry. But it also has a large effect on physical properties like melting point and boiling point. And the reason for that is, so take water, right? Draw the structure of water. As we did in class, you can all do that, right? There's water. But the thing is, you never have a single molecule of water anywhere. So it's snowing outside. I could turn the camera around. It's really pretty out. Those flakes aren't a single molecule of water. They're a bunch of waters all together. And how then, so we have all sorts of waters, right? How the water molecules interact with one another then dictates whether the physical state of the water is solid or liquid or gas, and how easy it is to transition between solid to liquid or solid to gas or liquid to gas. So anyway, this video will just run down some of the forces that are responsible for these, some of the factors that are responsible for these intermolecular forces. Okay, so the first one is electrostatics. Basically, all of these forces boil down to some sort of positive or partial positive charge interacting with negative or partial negative charge. So an electrostatic interaction is just exactly what it sounds with ions. So you might have, say, an ammonium ion, and then you would have, for example, maybe a bromide. Now we think about that as a salt. So that's ammonium bromide, which you would consider to be a molecule. But actually the reason ammonium bromide, which has a fairly low molecular weight, so ammonia, you get this by reacting. All right, so ammonia plus HBr will give you ammonium bromide. Ammonia is a gas, HBr is a gas, and yet it makes a white solid that melts at a relatively high temperature. And the reason for that is there's a lot of attraction between the positive ammonium ion and the negative bromide ion. So that's an electrostatic interaction. If you have a positive charge, a cation, interacting with a negative charge, an anion, that's a very strong force. You can even, it can be a strong enough force to give you an ionic bond, but even if it's not, so for example, something that might be a little less, you might have, this is still going to be a salt, that's ammonium tetrafluoroborate. The tetrafluoroborate, the negative charge is spread over a larger area. They can't get as close to each other, so that attenuates the electrostatic interaction a little bit, but it's still there. You'll often find in proteins, so in proteins sometimes you'll have carboxylates, and then the protein chain runs around here, and you have, say, a lysine residue that's charged. So at physiological pH in the body, an ammonium group is charged, carboxylic acid is deprotonated. And so you could get, this can hold the structure, this can hold the two loops together, the positive charge interacting with the negative charge. So anyway, electrostatic interactions are really strong, and they're very important. You're going to see them a lot in nature and molecules. All right, so the next one is a hydrogen bond. This is also going to be known as an H bond occasionally. And this one is, the best example then is the water that I was talking about. I'll talk about this right at the end, but by and large, melting point and boiling point scale with molecular weight. So the heavier a molecule is, the higher it boils, the higher it melts, higher temperatures. Water is pretty unusual, right, in that it's a very, very low molecular weight molecule, and yet it boils relatively high. It boils at 100 degrees C. That's the definition. So the reason for this is two water molecules can interact through what's called a hydrogen bond. And this hydrogen bond can be as much as 20 to 30 kilojoules per mole for a strong one, where a covalent bond is usually going to be around 400 kilojoules per mole. So, 5% of a covalent bond. 5% of a covalent bond is not enough to form a permanent bond. Okay, so in water, so then you also have, where was I going to do this? Okay. Right, if you think about the polarity of the OH bond, all these OH bonds, oxygen's more electronegative than hydrogen, so the electron density is shifted toward the oxygen's partial negative, the hydrogen is partial positive, and so you're basically getting the lone pair electrons on the partial negative oxygen interacting with the partial positive hydrogen. And like I said, you've got, in one snowflake out there, you've got probably 10 to the 15th, 10 to the 16th molecules of water. You get the idea. So basically all these oxygens and hydrogens form hydrogen bonds. Again, that hydrogen bond's about 5% of the value of a covalent bond. And so what happens is they form and break and form and break. If you could just take a picture of one molecule of water and follow it around, you would see it hydrogen bond to a molecule of water and leave, and hydrogen bond to another molecule of water and leave. You would see that happen billions of times a second. Water just hopping off. Of course, it happens more in liquid. It doesn't happen as much in gas because the molecules are spread out. In a solid, there's not as much motion, but there's still some. And so, like I said, these hydrogen bonds form and break constantly. And that goes for basically any hydrogen bond, not just water. So if we throw some ethanol into this, all right, so there's some ethanol. Ethanol can form a hydrogen bond. The oxygen, which is called a hydrogen bond donor, can bond to water, which is a hydrogen bond acceptor here. And then that can also hydrogen bond to another molecule of ethanol in the same fashion. So really, hydrogen bond is important for OH, NH, fluoride will hydrogen bond, and then things that are good donors. So carbonyls, carbon-oxygen double bonds, the lone pair on oxygens are good hydrogen bond donors. So again, the hydrogen bond donor is the atom with electrons, and then the hydrogen itself is the hydrogen bond acceptor. Amines, ethers, alcohols, ketones are good donors, and then alcohols, NHs, fluorides are good acceptors. So you get hydrogen bonds between them. All right, that's hydrogen bonds. The other two forces then are weaker. So the dipole-dipole force, I just talked about carbonyl. If you look at the charge in a carbonyl, you have a very strongly positive carbon, and you have a strongly negative oxygen. Some of that's inductive, right? Oxygen's more electronegative than carbon, so you get this polarity. But you can draw a resonance structure here. The pi bond is easier to have the electrons shift. That's a positive. You'll have to get used to my handwriting being pretty poor. So the resonance structure I've shown there for acetone, right? Dimethyl ketone is acetone. This resonance structure is not a great description of the molecule, but a significant player, with the result that that carbon is pretty positive, the oxygen is negative, and then these can line up. All right, they can line up where you've got the partial negative oxygen sort of interacting with the partial positive carbon. You get a whole series of these. And again, it's a fairly minor effect. However, if you compare acetone versus 2-methylpropene, right? Just about the same molecular weight, just about the same shape. The carbon-carbon double bond is much, much less polar than the carbon-oxygen double bond. And so this boils around 80 degrees, I think. Hang on, I've got that here. All right, sorry, not 80 degrees. I actually looked it up, so I know this. All right, so the boiling point of acetone is 56. Boiling point of isobutylene is -7. So about a 65 degree difference in boiling point just by making this bond polar. And again, that's just dipoles lining up. Okay. So the last effect is what we call the instantaneous dipole, the London dispersion forces. And what's going on there is, let's say we have, what is that? 1, 2, 3, 4, 5, 6, 7, 8. So this is octane, this is N-octane. And again, how is an N-octane molecule going to interact with other N-octane molecules? Well, there's no charge, so there's no electrostatics. There's no OH, NH. There's nothing with lone pairs. So there's not going to be a hydrogen bond. So CHs, it's important to note. So CHs can't hydrogen bond. Usually. There's a few exceptions, but if you just memorize that CHs can't hydrogen bond, you're going to come out a winner the vast majority of the time. So there's not going to be any hydrogen bonding in this molecule. There's no real dipole. So the CH bond is very slightly polar. And you're going to read that it's nonpolar. I'm probably going to talk about it being nonpolar. Obviously, carbon and hydrogen don't have exactly the same electronegativity. And depending on what the rest of the molecule is, the CH bond can be polarized. But in a simple alkane like this, the very slightly is enough to say that it's essentially nonpolar. So there's no real dipole, permanent dipole in octane. So what do you have? Well, you have what we call the instantaneous dipole, and that is at any given moment, right? There's a whole bunch of electrons swimming around here. So if we look at this, all the CHs are electrons. All the lines, as we talked about in class, are electrons. And they're in these orbitals that are diffuse. And so what can happen is, let's say in just an instant, all the electrons are up here and it's partial negative, and then down here is partial positive. And I mean this by the top of this molecule is partial negative. Just in an instant, for whatever reason, just random chance, the electrons pile up on one side of the molecule. That obviously can't hold for long. On average, the electrons are going to be all over their orbitals. But in one instant, the electrons might be up here. That would give you a partial negative charge on top of the molecule and a partial positive charge on the bottom. Well, in that instance, I need to do some erasing. I think I just erased something I need. Okay, let's put that closer up here. In that instance, then, there might be another molecule that, for whatever reason, again, has this instantaneous dipole, right? So all the electrons pile up on top, that leaves a partial positive on bottom, and you get an interaction between the partial positive and the partial negative. Clearly, that isn't going to be much of a force, right? It's a partial positive and a partial negative. That's not a huge electrostatic interaction. And it's instant. So in the next instant, the electrons may flow back, and now you get a repulsive force. So the instantaneous dipole, or the London dispersion forces, or van der Waals forces, are really weak, okay? But they're enough. So octane, you guys know octane, it's gasoline. You've seen gasoline, it's a liquid at room temperature. You pump it out of the tanks in the ground into the tank in your car. You can spill it. It actually hangs around for a reasonable amount of time. And the reason for that is it's a relatively large molecule. So if we compare this to water, okay, water with a much lower molecular weight, much lower physical size, has a boiling point higher than that of gasoline. Or it's about the same. And the reason is the hydrogen bond is a much stronger force. So even though that's a smaller molecule, the forces between them are stronger. Here, with just the instantaneous dipole, you need a bigger molecule. So here's the next bit, and really the last bit. So basically, to sum up, the higher you go on this scale, the more electrostatic interactions you have, the more hydrogen bonds you have. If you're comparing two molecules, one's got 2 electrostatic interactions and one's got 2 hydrogen bonds. The 2 electrostatic interactions will win out. That'll be a higher melting point, higher boiling point. If you have a hydrogen bond versus a molecule with just dipole interaction, the hydrogen bond, again, all else being equal, the hydrogen bond molecule will melt higher and boil higher. So, all else equal, the higher molecular weight has higher MP and BP. Okay, so all else being equal, the higher the molecular weight of a molecule, the higher its melting point and boiling point is going to be. So if you're comparing two molecules, molecule A and molecule B, they have equal intermolecular forces, but one has, they have equal types of molecular forces, so they both hydrogen bond and have some van der Waals. One has a much higher molecular weight. That higher molecular weight compound will be the one that boils higher and melts higher. Also, the more surface area you have, the higher the melting point and boiling point will be. And that's because this instantaneous dipole sort of depends on surface area. So really big hydrocarbons tend to cling to each other. Really small hydrocarbons, methane, it's a gas, ethane is a gas, propane's a gas, butane is a gas at room temperature. So small hydrocarbons don't boil particularly high. The bigger the molecule gets, the higher the melting point and boiling point. And so what you have to do is sort of assess what kind of forces exist in the molecule, how big the molecule is, what the molecular weight is, and then you can make a ballpark guess in comparison with other molecules you know. All right, we'll do this in class too, but if you want to check this out, there you go.